Hi all, and welcome to the Emergent Vision Technologies presentation on the benefits of 10, 25, 50, and 100 GigE Vision. I am John Ilett, President, CTO, and company founder, and I look to present our perspective on high-speed imaging. We are all familiar with Ethernet and GigE Vision for 1 GigE, and all the benefits it brings, and the benefits are listed here. By making only changes at the driver level, alongside of the existing high-speed network card technologies, we enable speeds up to 100 GigE and beyond, with equal or better performance, to frame grabber technologies, but at a fraction of the cost. But 100 GigE is available now, so continuing to stay a step ahead of the rest. As early as 2010, Emergent began shipping 10 GigE cameras and assorted technologies. Since then, others have followed with Me Too product. Emergent has kept ahead by releasing 25 GigE and now 100 GigE cameras, and we do hear rumblings of others following as before. A key differentiator is the effort Emergent puts into ensuring top performance and owning the whole acquisition picture, from camera to having your images safe at home in server system memory, with no frame drops and minimal CPU and memory utilization. Over the last few years, we have launched many new camera models, including 10 GigE, 25 GigE, and now 100 GigE cameras. 2020 saw an unusual spike as Sony and GPixel have launched many new sensors very suitable for our high-speed interface cameras. Sony is best known for its image quality, which was very good with their earlier high-speed Gen 2 image sensors like the IMX253, and more recently with their ultra-high-speed Gen 4 back-illuminated sensors like the IMX530. GPixel is best known to us for pushing the limits of speed and resolution, while maintaining a very good image quality. The GMAX series and latest G-Sprint series have taken Emergent to the next level in 25 gig and 100 gig camera models. On the revenue side, Emergent has nearly doubled in revenue year after year since 2010 to indicate the insane adoption rate of these new cameras and sensor technologies. In 2010, Emergent introduced the first 10 GigE cameras and received awards for our innovation. Since then, we have gone on to release over 60 area scan and line scan camera models ranging from 0.5 megapixel at 1586 frames per second to 50 megapixel at 23 frames per second. Some of the most popular models are the HR12000S for 12 megapixel at 80 frames per second using the Sony Gen 2 IMX253 sensor, and the HR3000S for 3 megapixel at 216 frames per second using the Gen 2 IMX252 sensor. Emergent was also the first to bring line scan sensor technology to the 10 gig interface, with the LR 8kg model achieving 137 kHz line rate with the GPixel GL0816 8K sensor. In 2018, sensor speeds took another jump, which justified the need for a higher speed interface. Emergent answered the call with 25 GigE cameras and received award recognition from multiple sources. Since then, we have gone on to release over 45 area scan and line scan camera models ranging from 0.5 megapixel at 1586 frames per second to 65 megapixels at 35 frames per second. Some of the most popular models are the HB25000SB for 25 megapixels at 105 frames per second using the Sony Gen 4 IMX530 sensor, and the HB12000SB for 12 megapixels at 192 frames per second using the Sony Gen 4 IMX535 sensor. Emergent was also the first to bring line scan sensor technology to the 25 gig interface, with the LB 8kg model achieving 200 kHz line rate with the GPixel GL0816 8K sensor. In 2020, sensor speeds took yet another jump, which justified a further need for speed. Emergent answered with 100 gig cameras, and was the sole recipient of the VSD Innovators Platinum Award over entries from all other major manufacturers of cameras, frame grabbers, accessories, and other machine vision products. We see resolution and frame rate as the major factors that define what high-speed imaging is, and we are now capable of virtually any resolution and any frame rate. At least we cover the fastest sensors in the industry with the now fastest interface technology in the industry. Most importantly is 100 GigE is available now and not months or years from now, as some gather around lower speed standards, waiting for improvement, ratification, and implementation. Shortly going into production are the following models. The HZ65000G, which provides 65 megapixel at 71 frames per second using the G-Pixel GMAX 3265 sensor. The HZ100G, which provides 100 megapixels at 30 frames per second using the G-Pixel GMAX 32103 sensor. And the HZ21000G, which provides 21 megapixels at a whopping 600 frames per second using the G-Pixel G-Sprint 4521 sensor. Our 100 GigE Zenith series by far exceeds the capabilities of cameras from other vendors and sets a benchmark which will be difficult to surpass for years to come. Accessories and integration play a very important role in the image acquisition framework, and Emergent takes responsibility for the complete acquisition solution and provides advice on well-tested architectures for most ultra-high-speed Ethernet applications. In addition to detailed integration and testing of the cameras, we invest heavily in integration and testing of all cabling options, switches, NICs, third-party processing and interface cards, GPUs, medium to high-end PC and server technologies, various OSs, and more. The purpose here is to provide the simplest integration effort for our customers. The customer should feel confident that with Emergent providing free consultation throughout their integration, that they would never encounter a problem that could not be resolved. Again, we are all familiar with the conventional GigE frame acquisition model. Even at 1 GigE, the Intel Pro 1000 based NICs were preferred for higher performance driver implementation, but still not optimal, and yet 1 GigE has dominated the industry. For those not familiar, it is known that such packet-based video technologies need to have the headers removed from the images before returning the complete image to the application. As we see here, this involves 1 times write of the data to system memory, followed by a read of only the video data from system memory, thus discarding packet headers, and finally a second write of this video data back into the contiguous memory buffer. This indicates a 3 times memory bandwidth requirement, which is the main reason why such implementations are low performance. At higher speeds, the network card technologies were ready, and many multiple NIC vendors have support for high-speed offloading while still maintaining the nearly 1/3 price advantage over a competing frame grabber. RDMA and ROCE are such technologies which enable true zero-copy transfers for performance equal or better than frame grabber technologies. We leveraged the underlying network card features related to RDMA and ROCE for the best possible image acquisition performance. In this case, the NICs can be programmed to be protocol aware and can place video in one contiguous memory location and headers as needed in another memory location. Things have only gotten better since 1 GigE, and performance is now as good as it gets. A video demo will follow in a few slides, but here is what a 24 x 10 gig volumetric capture camera system would look like with Ethernet versus CXP6. The Ethernet solution has 24 10 GigE cameras, a a switch for PTP synchronization, and multiplexing the 24 cameras onto dual 100 gig links. And finally, the single slot 100 gig dual NIC for placing the image frames in system memory. The equivalent CXP solution has the cameras, of course, but utilizes 3 times CXP octal frame grabbers to accomplish the same task. Some CXP customers suggest that this is not even practical. And here is the CXP case with fiber adapters for longer distances. In a follow-on slide, we will compare the BOMs for these two solutions for a common application, like volumetric capture. Here is what a 2 times 100 gig camera system would look like with Ethernet versus CXP6. The Ethernet cameras plug directly into the 100 gig dual NIC for a single slot solution. The CXP cameras need many multiple CXP cables to plug into the required 4 times CXP octal frame grabbers to accomplish the same task. And here again is CXP with fiber adapters for longer distances. In a follow-on slide, we will compare the BOMs for these two solutions. In past presentations, we had not presented CXP12 comparisons. CXP proponents were up in arms over this, so we now include the following cases. As we will see, there are still no advantages for the applications discussed. Here is what a 12 times 25 gig camera system would look like with Ethernet versus CXP12. The Ethernet solution has 12 25 GigE cameras, a switch for PTP synchronization, and multiplexing the 12 cameras onto dual 100 gig links. And finally, the single slot 100 gig dual NIC for placing the image frames in system memory. The equivalent CXP solution has the cameras, of course, but utilizes 3 times CXP12 quad frame grabbers to accomplish the same task. We note that there are currently no CXP12 octal grabbers, since frame grabbers, being FPGA based, are not yet capable of PCI Gen 4 speeds. If and when this happens, then expect an increase in power and cost related to the use of higher-end FPGAs. And here is the CXP12 case with fiber adapters for longer distances. We will note that this is in theory, as no fiber adapters like this exist to date, and total costs will be dictated by higher-end FPGA costs, which dominate the cost of the cameras themselves. Here is what a 2 times 100 gig camera system would look like with Ethernet versus CXP12. The Ethernet cameras plug directly into the 100 gig dual NIC for a single slot solution. The CXP12 cameras need many multiple CXP cables to plug into the required 4 times CXP12 quad frame grabbers to accomplish the same task. We will note again that this is in theory, as no cameras like this exist to date. The common theme here is that CXP adoption for higher speeds is very slow. And here again is CXP with fiber adapters for longer distances. We will note again that this is in theory, as no fiber adapters like this exist. The example in the top left here shows how an off-the-shelf powerhouse FPGA card can be directly connected to emergent 100 GigE, 25 GigE, or 10 GigE cameras. Many such third-party cards exist in the market due to the strong cross-industry standardization of Ethernet technologies. One application for such a card would be AOI, and in this case, all image processing is done on the card with its abundance of resources. Emergent can assist in accelerating your development with such a technology. The example in the top right shows how the same cameras can be integrated with GPU support. GPU Direct technology is available to eliminate host memory and CPU interaction. For those who followed the NVIDIA GTC sessions, you will note we make reference to BlueField 2, which is a major advancement in AI processing technologies, and will now provide NIC and GPU in a one-card solution. This is a game changer, and Emergent is primed for deployment. The example in the bottom left shows how customers can integrate our 25 GigE cameras with an NVIDIA Xavier. This is the precise architecture for a real drone system deployment. This same architecture is finding its way into machine vision and various medical applications. NVIDIA Clara AGX is a similar but higher performance alternative for such applications. And finally, the example in the bottom right is a 2 PCI Express slot solution for a complete 24 camera volumetric capture system, fully compatible with our eCapture Pro software solution. The system has been scaled to over 200 cameras at one customer site and 100 cameras at another site. This is the highest performance, lowest cost system in the market, thanks to the effort Emergent has put into development and integration of the latest Ethernet technologies. All triggering options are available with Emergent Ethernet cameras. PTP comes for free with a switch. Remembering the switch is also used to multiplex the cameras. Direct hardware triggering of the cameras is another standard method. Lastly, for the very rare cases where customers want to trigger cameras from the NIC, Emergent has its own dual-port 25 gig NICs and single-port 100 gig NICs with a front panel trigger port. Off-the-shelf FPGA cards, as seen in the previous slides, also have this I/O port functionality. We do have software to meet most of your needs with SDK and third-party compliant drivers. We draw special attention to our new eCapture Pro software, where we have full turnkey software for various applications such as AOI and volumetric capture for customers with limited development resources or no expertise in ultra-high-speed vision technologies. So we'll provide a short video demo at this point. This video represents the equivalent capture bandwidth of a 24 x 10 GigE camera system as described in application example 1. Please enjoy. So what we have here is Emergent 12 x 10 GigE HR12000S 12 megapixel cameras running at 60 frames per second, and 4 x 25 GigE HB16000SP 16 megapixel cameras running at 145 frames per second. The first thing we highlight here is the extremely low CPU utilization to dispel the myth propagated by some vendors when comparing Ethernet to other interfaces. The net result is an extremely high performance system that has 0 drop frames and missed saves to RAID storage, as well as 1 microsecond synchronization accuracy. In playback, we show one camera in the time domain. A nice feature of our new eCapture Pro software allows us to pause at a particular time and rotate through all cameras to show different points of view of the same instance in time, thanks to system synchronization. Referring now back to application example 1. This is a very important example, as with current CXP coax technologies, that even for shorter cable runs, you need 2 extra cards, which cancels out the cost of the switch we will use for this implementation. But note CXP here is a 3 PCI Express slot solution versus single slot for GigE, which poses server selection considerations. However, for longer cable runs, expensive CXP fiber adapters are needed, which makes this solution cost prohibitive. And note that even if and when camera companies adopt CXP over fiber, that they will still not be able to multiplex aggregate cameras through the switch, since there is no such thing as a CXP switch for this purpose. And this is a big advantage for Ethernet technologies. Referring now back to application example 2. In this case, 3 extra frame grabbers are needed, and many expensive fiber adapters if distance is needed. CXP over fiber improves this situation, but frame grabbers will never be able to compete with NICs on pricing. Referring now back to application example 3. This is a very important example, as with current CXP12 coax technologies, that even for shorter cable runs, you need 2 extra cards, which cancels out the cost of the switch we use for this implementation. But note CXP12 here is also a 3 PCI Express slot solution versus single slot for GigE, which poses server selection considerations again. However, for longer cable runs, expensive CXP12 fiber adapters would be needed, which makes this solution cost prohibitive. And note that even if and when camera companies adopt CXP over fiber, that they will still not be able to multiplex, aggregate cameras through the switch, since there is no such thing as CXP switch for this purpose, and this is a big advantage for Ethernet technologies. Referring now back to application example 4. In this case, 3 extra frame grabbers are needed, and many expensive fiber adapters are needed if distances are required. CXP over fiber improves this situation, but frame grabbers will never be able to compete with NICs on pricing. For this and the other examples provided, the CXP equivalents are more theoretical, since many of these cameras and accessories do not even exist, to further emphasize the slow adoption rate of CXP for high-speed camera technologies. Let's talk about CXP over fiber. So why was CXP over fiber decided upon? CXP standard and coax cable was never really suitable for high speeds. The CXP standard and coax cable was never suitable for long cable lengths. So how is CXP over fiber implemented? CXP over fiber needs all new hardware and firmware implementations. CXP over fiber steals the whole Ethernet physical layer and adopts all cabling options. CXP over fiber must still use dedicated FPGA-based frame grabbers, which leads to higher cost and lower performance due to the fact that the highest-end FPGAs do not currently support PCI Express Gen 4 technology. CXP over fiber cannot use Ethernet NICs and switches for all associated benefits, such as multiplexing. And CXP over fiber still uses the CXP protocol, discarding the well-established Ethernet protocol. And there's really only very small differences in the protocols, so no significant gains. When will I see CXP over fiber product? A very small handful of companies are involved in the specification, and products are coming slowly both on the camera and frame grabber side. Initial products are based on 40 gig QSFP+, which is the simplest of implementations since it simply creates 4 times 10 gig lanes. The major switch vendors consider 25 gig as the new 10 gig, 50 gig as the new 40 gig, and then there is 100 gig. 40 gig is already being considered outdated technology, with 25 gig, 50 gig, and 100 GigE providing the best density and price performance ratios. Even slower will be the adoption of 50 gig, 100 gig, and beyond, which is already available now in Emergent Ethernet-based cameras with complete accessory portfolio. 25 gig has already been available for 4 years, and 10 gig for over 10 years. When considering the benefits of GigE Vision for high-speed imaging, one might wonder if there were sufficient benefits for launching a new standard like CXP, when GigE Vision cameras clearly offer the best choice for a high-speed interface for machine vision applications. Considerations include ultra-high data frame rates capable of 10 gig, 25 gig, 50 gig, and 100 gig. Same CPU and memory utilization using standard built-in NIC functionality. Stable image acquisition timing. Image acquisition does not slow down processing, and the protocol makes very little difference. GigE can do virtually anything CXP can, and sometimes more, such as multiplexing, as we've seen. CXP with CXP over fiber no longer has power over cable spec, which loses one big benefit that CXP had. CXP is converging quickly to GigE with physical layer adoption. Longest cable lengths are certainly a benefit of GigE. And IEEE standard support for best management and the widest adoption. All of these benefits are available now. So how has GigE technology adapted to accomplish all of this? It's literally only been firmware and software changes to the off-the-shelf NICs to provide this higher performance and lowest cost benefit. How has CXP technology adapted to accomplish the same? A completely new interface, protocol, hardware, firmware, standard managed by a small group of proponents within the isolated machine vision industry. Completely new frame grabbers, firmware, and software to support coax-based CXP. Completely new frame grabbers, firmware, and software to support fiber-based CXP. Our cameras are everywhere you care to look. We dominate in certain spaces where adoption rate is more rapid. We believe other spaces will follow, especially where factors such as cost sensitivity, system simplicity, and time to market are at play. Hi all, and thank you for joining us for the Emergent Vision Technologies presentation on the benefits of 10, 25, 50, and 100 GigE Vision. I am John Ilett, President, CTO, and company founder. Please feel free to contact us if you have any questions, and we look forward to speaking with you soon. Here is how you can contact us, and we appreciate you taking the time to view our presentation. Thank you.